Linear data structures collapse under composite workloads. In a sorted array, searching a million records is incredibly fast, but inserting a new one requires a catastrophic memory shift to maintain order. Conversely, an unsorted array allows instant insertions, but suffers from painfully slow searches. To bridge this gap, combining logarithmic search with dynamic insertion, data must evolve from a flat line into a multidimensional hierarchy. Enter the binary search tree.
A binary search tree is defined by a mathematical law known as the ordering invariant. For any given node, values in its left subtree are lesser or equal if duplicates are permitted, while values on the right are greater. This simple rule transforms a web of pointers into a high-speed geometric search engine. Topology dictates destiny. In an ideal balanced state, the tree height scales logarithmically. You can search 1 billion records in just 30 steps, giving O of log n performance. But in a naive, unbalanced tree, if data arrives pre-sorted, it mutates into a degenerate linked list. Performance crashes to O of n, turning a microsecond retrieval into a massive system bottleneck. Modern applications prevent this using self-balancing variants like AVL or red-black trees.
Because trees are non-linear, we require systematic traversal algorithms to read them. Pre-order is perfect for serializing data. Post-order is a bottom-up approach, essential for safely deleting nodes from memory without losing pointers. But the true engine of the search tree is the in-order traversal. The in-order traversal visits the left subtree, then the root, then the right. Because of the ordering invariant, this specific sequence mathematically guarantees that the output will be perfectly sorted in a non-decreasing order, naturally accommodating potential duplicate values. It effectively flattens a two-dimensional geometric structure into a one-dimensional sorted list.
Translating this to code reveals the elegance of recursion. The function calls itself to dive deep into the left branches, processes the node, and then dives right. However, each recursive step consumes space on the call stack. A deeply skewed tree can trigger a catastrophic stack overflow, requiring advanced iterative techniques with explicit stacks to resolve.
Despite their mathematical elegance, basic search trees clash violently with modern hardware constraints. A single node requires up to 48 bytes just to store an 8-byte payload, leading to severe pointer bloat. Furthermore, traversing scattered pointers destroys spatial locality, causing constant CPU cache misses. This physical reality forces high-performance systems to abandon pure search trees for hardware-optimized variants like B trees.